All right, as of now, we are gone live as usual, so it's being recorded. And like I said, we have 1 more minute to see if the missing students will show up. Then we will start. And then we didn't have anybody show up, so we will just kick in. So again, like I said earlier, this lecture is about approximating functions with polynomials. So what is that about? Say we have a function f of x that needs to be approximated. I wanted to write estimated, but it's the same thing, but by means of a polynomial of degree n. So you have a function f of x, and you want to approximate that function using a polynomial of degree n. And you want the assumptions let's call that Pn of x. You have the assumptions that f of x so f of a is equal to Pn of a, and all derivatives are equal where a is the center of the polynomial we are using. So you have a polynomial that is centered at a point A that is given, and you want to use that polynomial to approximate the function that you have. What are the conditions for that to be possible? And say here we say you need this, that the value of the function at the point A is same as the value of the polynomial. All derivatives, because k less than or equal to n, all derivatives up to n of the function are equal to the derivatives of the polynomial. In that case, yes, we will say that this polynomial is the approximation of the function, and that approximation is called a Taylor approximation, Taylor polynomial of degree n. Right? So using this, we can derive that we got one. The polynomial that we are looking for to approximate is f of a plus f prime of a times x minus a plus the nth derivative at a times x minus a to the power n divided by n factorial. So for this condition to be satisfied, the polynomial Pn of x needs to have this form. We can easily prove that, but it's not necessary. Our job here in this class is, first of all, to learn how to find that polynomial with this definition and how to use it to estimate the value of a function. Because if you can't hear me, make sure you check your volume. We check this before starting the class. So this is what the polynomial Pn is going to look like. And it's going to be used to estimate the value of a function around the point A. For instance, when A is something that you can find easily the value of f for, and you have a number x, if x is close to A, this formula can be used to estimate the value of f of a, the value of f of x, when f of a is easily computable. What does that mean? For example, let's say we can say estimate square root of 4.02, for example. If you're asked to estimate square root of 4.02, of course, today when we say that, you just take your computer or your calculator and punch those numbers in and you see what it is, right? But guess what? When there was no calculator, how would you think somebody would estimate that? All right. And so here, if I want to estimate the value of square root of 4.02, I see that this is, the function is f of x equals square root of x. X is 4.02, and the number a that is close to this 4.2 that I can easily find the square root of is 4, right? That's it. So a is 4, and I can easily find square root of a, which is 2. And so I'm going to think of that formula. Let's say we do this just for n equals 2, for example, and we will say P2 of x is equal to It was like 3 even, okay? Not to get people confused with the 2 that is for the polynomial and the 2 that is coming out of there. So this is
paper
equal
up a
to,
little bit.
yep, thank you. So P3 of x is equal to f of 4, because that's a, plus f prime of 4 times x minus 4 plus second derivative at 4 times x minus 4 squared over 2 factorial plus third derivative at 4 over 3 factorial x minus 4 cube. That's what this formula means. So you add them all the way up to that, divided by factorial 2, and each of the terms that is coming is over factorial of the number of derivatives. So this is next f second derivative over factorial 2, third derivative factorial 3, fourth derivative factorial 4, and so on. And so now you find that those things for this function. So f prime of x, that's the derivative of this function, that is 1 over 2 square root of x. And so f prime of a, you find it, 1 over 2 square root of x of a. A is 4, so that's 1/4. Then you get the second derivative that is necessary. Derivative of this derivative, that is minus 1/4 x to minus 3 halves. So that's the derivative of this. And then you find the value at a, and a is 4, so that is minus 1/4, 4 to the power minus 3 halves. That is minus 1/4, 2 to the power minus 3, which is minus 1 over, and that's going to be 8 times 4, 32. And then you get the third derivative, which is derivative of this derivative. Minus 3 half comes in, that becomes 3/8 x to the power minus 5 halves. And the third derivative at a is 3/8 4 to the power minus 5 halves, which is 3/8 2 to the power minus 5, which is 3 over 2 to the power 5. What is it? 32. So now you get 32 times 8. So that is 3 over, and 32 times 8, that's be 8 times 2, 16, 8 times 3, that's 204, and 1, 205, right? So that's what you get. And now you say P3 of x equals f, yes, one thing is missing, f of a, of course, is square root of 4, which is 2. So P3 of x is f of a, that's a formula that is already written here, so we can just write that answer. So f of 4, that is 2, f prime of 4, that's 1/4, times x minus 4 And then second derivative, that is minus 1 over 32 divided by 2. So minus 1 over 64 times x minus 4 squared plus, and then third derivative, it's 3 over 256. So that's 3 over 258 divided by factorial 3, which is 6. So that's 3 over 258 times 6, which is factorial 3. Times x minus 4 cube. So this is the polynomial of degree 3 that is used to approximate the function. Then we can multiply here, divide by 3 and multiply this 2 by, that's going to be 516. So minus 1 over 516. So that's P3. Then if I ask for P2 of x, then you got to write the whole thing and start at 2. P2 is 2 plus 1/4 x minus 4 minus 1/64 x minus 4 squared. If I want P1, it's going to start first order, 2 plus 1/4 x minus 4. And P0 of x, it's just that first one. So these are the rules. So P0 is just that first term, f of 0. P1, it's f of 0 plus f prime times x minus a. P2, you add the next term. Notice that the difference between this one and this one is the next term. The difference between P1 and P2 is the term with the square, and the difference between P2 and P3 is the term with the cube. And there is no other work you need to do on this. This is all you need to write down. You don't need to now continue opening the parentheses and doing some calculus. You don't need that. Now, to go back to the original question, if we wanted to estimate square root of 4.02, if that's what we wanted to do, that means that we need to plug in x equal 4.02. That's what the question means. So you need to go into this formula and replace x by 4.02. If we say find the linear approximation, please listen carefully at this point. If we ask you to find a linear approximation, that means this. We need P1. When we ask for P1, we ask for linear approximation. So this is called linear approximation. And this is quadratic approximation. So in some problems, you might find the linear approximation of this, right? And that's what you do. Now, for this specific problem that we had at hand, let's see how we would end the problem. It would be just plugging the numbers. That's it. Just be plugging in the numbers. If we are looking for linear approximation of square root of 4.02, then we are going to take P1 of x, which is 2 plus 1/4 x minus 4. And so P1 of 4.02 is what we need, 2 plus 1/4 times 4.02 minus 4, which is going to be 2 plus 1/4 of 0.02. And divide this by 2, that's 0.01. And 0.01 divided by 2. So that's what you would get. All right. Does that make sense?
Yeah, that makes sense.
And that's all the question is about. You don't make it more difficult when you find it. So if we say quadratic approximation, and that is going to be P2 of x, and we have P2 of x right here. So P2 of 4.02. And if you remember what I told you earlier, this part is exactly what P1 is. So I can just report that number there, 2.005 minus 1/64, 4.02 minus 4 squared. Because that beginning is exactly what we just computed as P1. P2 is P1 plus the next term. And so here, that's 2.005 minus 1/64, and then 0.02 squared, which is 0.02. Okay. Any questions? Is there any question about this? Now let me give you this other example. Find P0 of x, P1 of x, P2 of x, P3 of x for f of x equals cosine of I of x. So the function is cosine of x or 5x, and I want you to find P0 of x, P1 of x, P2 of x, P3 of x, and I'm leaving the formula of Pn of x right there. So you can use. Anyone ready? Want to share something, Matthew?
I'm still looking at it. Yeah.
Nick?
Yeah, I can go.
All right. First of all, the first one, it's P0 of x. What
Yeah.
would P0 of x be equal to?
For that one, I got cosine 5a.
Formula, first of all, that's f
Oh.
of a.
Yeah.
All right. Which is
Cosine
cosine
5a.
of 5a. And say I give you a equals pi over 2. So P0 will be, what's cosine of 5 pi over 2? That's 0. So P0 of x in this case is just 0, no matter what x is. That's P1 of x.
For P1 of x, that would have been f of a plus f prime of a times x minus 4.
Minus a, right?
Or, yeah, minus a, my bad.
All right, so that's the formula. You got to be able to get that formula first before being unable to do the work if you can't. So now you got to find f prime of x. That's f of x. F prime of x is, what's the derivative of cosine 5x?
5 sine 5x. Negative 5 sine 5x.
Mm-hmm. You can clearly see that what's going to be the problem in this part is if you don't know your derivatives, you're going to be in deep trouble. Derivatives and integral, both of them. And so here f prime of a, and a is pi over 2, that is negative 5 sine 5 pi over 2. And sine of 5 pi over 2,
Would that be 1?
that's 1, yes. So that's negative 5. So this P1 of x is 0, that's it, minus 5 times x minus pi over 2, that's it. That's what P1 is, minus 5 times x minus pi over 2. P2 of x, I can say that's just P1 of x plus and now here you need the second derivative, so you get that second derivative. Second derivative is?
Negative 25 cosine 5x.
Correct. And the second derivative at pi over 2, that's be negative 25 cosine of 5 pi over 2 again is 0. So this is equal to negative 5 x minus pi over 2 plus 0, so nothing. So you can see that here P1 is equal to P2 because the coefficient of x minus pi over 2 squared is equal to 0. And P3 of x, that's P2 of x plus third derivative at a over 3 factorial x minus a cubed. That's minus 5 x minus pi over 2. And then you got to find that third derivative. And that's here. 5 times 25. That's 125 sine of 5 x. I already plug in pi over 2. And then the third derivative at pi over 2. 125 and sine of 5 pi over 2, you guys gave me that earlier, that's 1, so that's 125. So here it's going to be plus 125 over factorial 3 is 2 times 3, 6. That's it. There you have P0, P1, P2, and P3. So these functions are called actually Taylor polynomials. So this is the Taylor polynomial of degree 0 for the function f, Taylor polynomial of degree 1 for the function f, Taylor polynomial of degree 2 for the function f, and Taylor polynomial of degree 3 for the function f that we have centered at pi over 2. You always need to have a center when you're finding the Taylor polynomials, and the center is the a that you had defined in the question. Now, of course, as for this series that we had, when we had an estimation, the obvious thing to ask about is how accurate is that estimation? What's the maximal error that I make when I'm using that polynomial to estimate the function, right? And so we say that when the next derivative exists, and is continuous, the remainder Rn of x. Remember, we always put the remainder as Rn, and now we put of x because we have a function of x. Rn of x is n plus first derivative at some point c times x minus a to the power n plus 1 over n plus 1 factorial, where c is a number between x and a. And we do say between x and a without putting signs less than or equal because we don't know which of the two numbers x and a is less than the other, right? So x is c is a number between x and a. So when the next derivative exists and is continuous, then we can prove that the remainder can be written as n plus first derivative at some point c, that is between x and a, divided by n plus 1 factorial times x minus a to the power n plus 1. And this formula is often used to find an upper bound on the error. If we can bound this derivative, because we don't know the point c. Here, this thing says at some point c. We don't know that point c, and it's just no way in general we can find the formula of that point. But if we can find a boundary, if we can find an upper bound on this derivative on the interval between x and a, then we can find an upper bound on the error. And therefore, as we did for series, find the value of n such that that error is less than a given number. And therefore, we will know how accurate is the estimation when we're using that number n. Am I making sense on this? All right, so let's see that on one example. Let's say we take here a very simple function, f of x, that we actually know, right? That will require no work at all. Let's say we take f of x equals x, okay? Just to stupidly waste time on that and see what's gonna happen. So we take a equal 1 as well. So f of 1 is 1, and p1 of x is f of 1 plus derivative f prime of 1 is 1 also, because f prime of x is 1 for all x. So that's 1 plus x minus 1. So that's p1 of x. So in this example, we would say r1 of x is n is 1. That would be second derivative at some point c divided by 2, which is 1 plus 1 factorial times x minus 1 squared. But yet, what is the second derivative here equal to? The first derivative is always equal to 1. What's the second derivative?
That'd be 0.
0. So this thing is telling us that the remainder will be 0. And that is true, right? Because p1 of x is actually 1 plus x minus 1. That's x, which is f of x. So p1 of x is equal to f of x always in this example. So c in this case is any number, because the derivative is going to be equal to 1 at any number, at any point between x and a, right? The second derivative is equal to 0 at any point between 1 and x. Does this example make sense? Okay, now let's look at a second example with a quadratic. Let's say f of x equals x squared, again, a equal 1. F of 1 is 1. F prime of x is 2x. And second derivative is 2. And so f prime of 1 is 2 times 1, 2. And so p1 of x is f of 1 plus f prime of 1 times x minus 1. And r1 of x is the second derivative at some point c over 2 times x minus 1 squared. And the second derivative at any point is 2, right? Are we okay? All right, so that's going to be 2 over 2. So the remainder for this one, according to that formula, is r1 of x equals x minus 1 squared. That's the remainder when you're using P1 to estimate f of x centered at 1. And P1 of x in this case is 1 plus 2 times x minus 1. Now, why am I taking these examples? To show you that there's actually, when the functions are perfect, you can see clearly without any extra work that those things work. Now, you need to check that P1 of x in this example plus R1 of x, what is this supposed to be equal to? Any guess? Do you want to guess, Nick?
Would it supposed to be equal to 0?
P1 is the estimation. R1 is the remainder. What is the sum equal to?
Wouldn't it be equal to f of x?
F of x, yeah. Because we are estimating f of x and r of x is the remainder. So if you add the estimate to the remainder, what we get is f of x. So on this example, you can perhaps check that you will have that perfect equality, right? So you can have here r1 of x plus p1 of x is equal, that's x minus 1 squared plus 1 plus 2 times x minus 1. And that is like a squared plus b squared plus 2ab, which is nothing but a plus b squared, x minus 1 plus 1 squared. By the formula, a squared plus b squared plus 2ab equals a plus b squared. And that is x minus 1 plus 1 is x, that's x squared, and x squared is really f of x. So yes, on this example, you can see that yes, that works really, that r1 of x is really the remainder when you use P1 to estimate f of x. So that's why I was picking these examples, not for the work that is in it, but to show you that you can have that perfect equality without having to look for C in the simple examples when the function is a polynomial. It is quite simple to see that. Okay, but it involves a lot of work to prove that Rn of x has the formula that is given, And we are not spending class time to prove that because our goal is mainly to use those things in this class, understand how they are used, right? Any questions? Now, example 3. For f of x equals square root of 1 plus x, estimate f of point 1 and f of point 4. Find a formula for R1 of x. And then here, you are going to estimate using P1 of x. So that's sort of repeating the work that we just did for point 1 and point 4 and the function square root of 1 plus x. And here, when it's given like this, point 1 and point 1, you can feel here that a is 0. In this problem, a is 0, okay? And please complete the activity. I'm saying this to those who are off cameras. It is important to do this as we do because it gets you prepared. And please, anybody ready, let me know.
Dr. Longo, I have a question for the example.
Yes, sir.
So for the equation for the remainder, do you want us to provide a C value too?
No, just write the formula with C.
Oh, okay.
Mm-hmm. Often what we do is, after writing the formula, find an upper bound on it. But I'm not asking you to do that here. All right, so please. Let us do this, otherwise we'll not have time. We have 15 minutes left.
I can share what I did.
Okay, so we need first the formula. We need to find the formula for f of 0.4. Now first we start with 0.1.
So for the first thing I did was I defined what f of a was.
Yeah, that
So-
can be done in general for both things, okay?
Okay.
So we can actually leave that out first, and we find you get f of a, that is 1, right?
Yeah.
F prime of x, what is it? Derivative?
I had that as 1/2 x plus 1 to the negative 1/2.
Yep. And then second derivative, we need it as well.
I had that as negative 1/4 x plus 1 to the negative 3/2.
That's right. And so we find f prime of 0, which is a. That's 1/2. And then the second derivative at c, it's minus 1/4 c plus 1 3/2. And now we can find P1 of x in general.
That would be f of a plus f prime of a times x minus a.
In this case, that is 1 plus 1/2 x minus 0. So that's just 1 plus 1/2 x. And then R1 of x is second derivative at some point c divided by 2 factorial x minus a squared, and that is negative.
Sorry.
Sounds right, it's good. Over 2 factorial is 2, 2 times 2 is 2 times 4 is 8. C plus 1 to the 3/2 x squared. So that's what R1 of X is. And now P1 of 0.1 is nothing but 1 plus 1/2 0.1. That's 1.05. And P1 of 0.4 is 1 plus 1/2 of 0.4, which is 1.2. Questions? Any questions? All right, so we'll be assuming that this is what we have learned today, how to get the Taylor polynomials, how to get the remainder, and how to use that to estimate the value of a function at a given point. In this example that we have here, if we wanted to give a bound on the estimate here, so a bound on the error, for x equal 0.1, you would have absolute value of R1 of x equals, you put the absolute value on that, that becomes 0.1 squared over 8 times c plus 1 to the power 3/2, which is 0.01 over 8 times c plus 1 to the 3/2, where 0 is less than c, less than 0.1, because we say that c is between x and a. X here is 0.1, a is 0, so c is between 0 and 0.1. And we find an upper bound on this for the values of c between 0 and 0.1. And we can see that here, this function here, this function of c is a decreasing function of c. Decreasing function of c. So this function is a decreasing function of c. And because it is a decreasing function of c, we are going to plug in the smallest possible value of c to find the upper bound on this. So it's always going to be about your knowledge of the function that you get right here to find what the upper bound is. So here, this is a strictly decreasing function of c. So when a function is decreasing, that means the graph goes down like this. So the highest value of the function is at the smallest value of the variable. That's why here we are going to pick 0 to get in there to find the largest value of the function, because it is decreasing. Why is it decreasing? Because we know the property. This is c plus 1 to the power 3/2. 1 over that, it's a decreasing function. And so we are going to plug in 0 and say absolute value of R1 of 0.1. So here we could put 0.1, right? Because we are using 0.1. It's less than equal to 0.01 over 8. And then we plug in the largest value of c, which is the smallest value of c, to get the largest value of the function. And here it's 0. We plug in 0, we get 1 to the power 3/2. So this thing is 0.01 divided by 8. So when we use this formula to estimate P1, to estimate square root of, am I doing this the right way? To estimate f of x being 0.1, which means square root of 1.1. So this is an estimate of square root of 1.1. And the error that we get on it is smaller than 0.01 over 8. If we divide this, what we're gonna get? So this is almost 0.02. Around it to 2. It's not really up to 2, right? It's 0.001 something, right? So we will have at least 2 correct decimal points. So these 2 numbers are correct here. So the absolute error is less than that. And if you take 0.04, sorry, 0.4, then absolute value of R1 of 0.4 can be less than 0.4 squared over 8 c plus 1 to the 3 halves. And for the same reason, here, this thing is going to be less than equal, because that's still that c plus 1 to the 3 halves. And the interval just got larger, but still it's a decreasing function. So the maximum is still going to be around that 0. So 0.0. Less than 0.4 squared over 8. So we can divide here. So 16, it's gonna be 2. So the error for this guy, you can see that when you get away from 0.4 being larger than 0.1, the error that you're getting is smaller. The further you get from that, from the 0, the larger the error you get. So this error is significantly larger than that one, right? You can see 0.02 here, 0.002. All right, that's it for today. Next time we will do other things. Again, thank you for finding the time to show up, braving the weather for us to have this lecture today. I know that there are places where there is no electricity at this point, so it's really a hard time. See you guys next time. And please do what is necessary. We have our test next week. So see ya.
Thank you, Dr. Longo.